Hi everybody, this is Andres. This is my lab report. I'm in section M, and the objective of this lab was to study and model the motion of falling objects. Here I am holding a paper ball. I am dropping it to the ground here. I set tracker to start right after I let go of the ball and to end right before the ball hit the ground. I chose my origin to be the center of the paper ball, and I used my calibration stick on this sheet of paper I put here and looked up the length of it in meters, which is 0.2794 meters, and I tracked its path. This is going in the negative y direction, and I also modeled the motion on Python. I set the initial conditions here for the paper ball to be 0.0045 kilograms, which is the standard. The initial position was 0, 0, 0. It is at the origin, as you can see here on tracker. And for the initial velocity, what I did was I took the second point here, negative 0.052, and divided it by the time, delta t, and that gave me an approximate initial velocity here. I chose delta t to be small, 0.005, in comparison with my total time of roughly 0.47 seconds. Specifically in this model, I did not have a drag force, therefore my B was equal to 0, and my F net was just force due to gravity. I used the momentum principle, where V final equals V initial plus F net times delta T divided by the mass, and the position update formula, where position final equals initial position plus velocity times delta T. I have an arrow here for the force due to gravity, so you can see it as a red arrow when it runs. There it is, it's falling. I modeled this on Excel. This is the blue represents the tracker information from the experiment, and the red represents the Python model. Obviously, the model, since it did not use the drag force, it fell faster than the experiment would have predicted. So I went back into Python and I set the constant of proportionality to be B equals 0.0023. I played around with it and I found this concept of proportionality to work well. And this the drag force is actually this constant times the magnitude of the velocity squared times the unit vector of the velocity, so in that direction. So therefore the net force is the F drag plus F grav. All the rest of the initial conditions were the same. And here's the motion with the drag force. The black arrow now represents this drag force, and it gets bigger as the drag force increases due to the magnitude of the velocity increasing. And I compared that to my experiment and found that it matched up quite nicely. So therefore, obviously on the paper ball, drag force was a big factor. I also recorded a video of me dropping my shoe. Again, I chose it to move in the negative y direction. Same calibration. Chose the origin to be the center of the shoe and track the shoe through its center. I started right after I let it go, and the end of the clip is right before the shoe hits the ground. I also did a model of this in Python without the drag force, again of B equals 0, and initial conditions, the mass of my shoe was approximately 0.45 kilograms. I chose the initial position to be the same initial position as in the video, and I found the initial initial velocity, the same way I did it with the paper ball. I also did the same thing with the paper ball with the momentum principle to update the velocity as well as the position. And here on Excel, there actually is much better agreement with the experiment and the model without the drag. So obviously the shoe experienced much less drag force. However, to make it even more accurate, I did add that very little drag force in my Python model and found it to be around 0.0001. So obviously it's much smaller. Again, the same initial conditions, and again the black arrow, which is pretty much almost non-existent compared to the red arrow. And you see here, this is the with drag, the model now fits the experiment even better, but very little drag force was obviously needed. So in reality, the shoe experienced very little air resistance. For the what does it mean, I took the paper ball model and plotted velocity versus time. Without drag, the velocity changes at a constant rate. However, with drag, the velocity seems to level out towards the end, and so I predict a terminal velocity for the model predicting drag. For the what if, I went back to my Python model, and if it was thrown downward with initial velocity, I incremented the initial velocity to -3 to represent that reality. With no drag, there was no change in the velocity except for the fact that it was all shifted downward. However, for the model with drag, you can see it levels off much quicker than the than the other model with drag. Therefore, if it was thrown downward, I predict it would reach terminal velocity much quicker.